All right, so we're coming back with all your GPIO registers, right? So you put your ports, your tris, and your lats. So now I have connections to them. So from now on, every time I need to use any of this, I just simply include this file into my code. That will fix any problems, okay? So what I'm going to do now is that I'm going to add all the registers that have something to do with my external interrupts, okay? So I'm just going to put a heading here, and I'm going to go external interrupts. So to work with the external interrupts, I am going to need access to my intcon, intcon2, and intcon3, right? So I'm going to do it structure-based because I don't want to remember the location of the circuits. I just want to get them by name. So I'm going to go struct underscore intcon All right, so I'm going to go to chapter 9. There's my intcon right there. I'm going to make this bigger. Always remember to start from the right side, okay? So I'm going to start from the flag. So I'm going to go int RB IF 1 bit, int INT 0 IF 1 bit, int timer 0 IF 1 bit, int RB IE 1 bit, int INT 0 IE 1 bit, int timer 0 IE 1 bit, int PE IE 1 bit, GIE 1 bit. Stop. Okay? So you get your connections made, right? Most of your compilers, by the way, we have this already predefined. 90% of the time, your compilers will get this already predefined. I'm using this choice because I want to make sure that you understand how are we connecting and why are the circuit working this way, right? This is not necessarily the most effective route, but it's the best route for you to be able to see how your circuit is operating. All right? So this is nothing more than the connection. It's just a recipe. Just a recipe. So you always begin with underscore the name of this guy in lowercase. Like I said in the beginning, you don't have to use the underscore. I use it because I have my own biases on how object orientation works in my mind. So you don't have to use this underscore. I use it because it helps me keep things in my mind right. You can call it anything you want, but it's a good idea to keep it in lowercase because data types usually show up in a lowercase format. So, and then after you're done with that, I create the connection. All right. So I'm going to do the connection by hand. So it goes struct intcon, and then I go pointer intcon, and then I find FC, I don't remember where it was, page 65, I think it's FC1 or something like that, I don't remember. Intcon, where are you? FF2, semicolon, okay, there. See that? So this gives me access now through intcon. Using intcon, I gain access to these circuits. Right? That's the idea behind it. And so usually what I tend to do is I want to make sure that when you count, make sure you have 8 circuits, 8 bits in total. So I got 1, 2, 3, 4, 5, 6, 7, 8. And this is the guy to the right, the least significant bit. And so it is in the proper sequence so you don't get things mixed up. Okay? Make sense? I'm going to do intcon2 now. So I'm going to go struct underscore intcon2. And so I'm going to go back to chapter 9. Here is intcon2. RBPI all the way to the right. See that? And then I have this guy that is not used. You can give it any arbitrary name you want. So I'm going to call this guy unused or not used or something like that. And so the same thing with this guy. All right? Okay, so here we go. So I'm going to put this at 90%. All right, so here, int con2, 1 bit. RB, IP, 1 bit. Int unused, 1 bit. Int TMR 0, IP, 1 bit. Int not used, 1 bit. Int INT EDG 2, 1 bit. Int INT EDG 1, 1 bit. Int INT EDG 0, 1 bit. And then we got RBPU, int RBPU 1 bit. And then you go struct int con2, int con2, 0 hex FF1. Okay? And that creates the connection with the name of all the circuits so that now it follows the pattern that we're learning embedded, right? You go with circuit, arrow, so go register circuit, register arrow circuit equals to whatever you want to do with that circuit. Okay? So keep going, do int con3, get that done as well. So I'll run it. Remember that this is not a main code. You cannot compile this. You can only save it, okay? So I'm just going to do struct int con3. Go int. Here is int con3 right here. So we go from the right, starting from the right. INT1 IF, 1 bit. INT2 IF, 1 bit. Int unused, 1 bit. Int INT1 IE, 1 bit. Int INT2 IE. Int not used, 1 bit. Int INT1 IP, 1 bit. Int INT2 IP, 1 bit. Finish, and then you go struct int con3 star int con3 FF0. Okay? So those are the connections. So you notice the pattern is just the word struct, that name in lowercase, and then you go, each of these names get 1 bit, and you name them in that sequence all the way till the end, and then semicolon, right? So that gives you your library. Now, I'm going to just now work a little bit on last week's ADCON1 because this ADCON1, we're going to be using it all the time from now until like pretty much the end of the class. And so I want to make sure that we gain access to this ADCON1. So I'm going to take a gander. Yes, go ahead.
Aren't the unused zeros?
No, 1 bit. They occupy space. So this is bit 0, bit 1, bit 2. So this occupies a full bit even though it's not there. So you can't make it 0 bits. Make it 1 bit so that it occupies the space. All right. So now I'm going to make a division once again in my library, and I'm going to put analog to digital unit. So I'm going to go here and type analog. By the way, I'm going to be loading this online in a little bit, so you have it. Analog to digital converter unit. And I'm going to go struct ADCON1, which is the circuit that I want to work on. I'm going to show you what that circuit is. We're kind of like going really fast right now. Is this guy, this circuit. So we studied this guy last week, so I'm just going to make a connection to it. So we go int PCFGX 4 bits, int VCFG0 1 bit, int VCFG1 1 bit, and then int unused 2 bits, and then I create my connection struct ADCON1 star ADCON1 equal FC1. Okay, so this is our startup. All right, this is where we're going to begin. And if you really think about what we're doing, I'm just kind of like creating a map of my circuits. It's just like, look, I don't want to remember the position of these circuits. I don't want to know where they are located anymore. I just want to create a map once. And once I know that this map is good, from now on I can use the names, knowing full well that I'm referencing the right circuit. It is actually very good for troubleshooting, because if something goes wrong, you don't have 5 guys in your shop making pointers every week. Can you imagine the probability of making a mistake? But if I make a library once, and we all know that it works, that means that the connection to the circuits are to be trusted. And then now I can just concentrate on blaming people, which is like my favorite pastime. Make sense? All right. Okay. So I'm just going to save this. So I'm going to go File, Save. So go File, Save. I'm just going to now forget about this for a little bit. Okay? So I'm going to go File, New. And I'm going to go away from the library and into the external interrupt. Yeah, go ahead.
Before you said for ADCON1 DCFG, put it 0 or put it
Where? Here?
No, right beside that. No, right.
Down one row.
Here?
Yeah.
Probably that's an O. 0. There it is. Yeah, it was an O. Thank you. That means that down the road when we have to move this, I won't be able to get to it. So thank you very much. All right, so I'm gonna just, you can now close this and just create a new one. So I'm gonna go New, and I'm gonna create a new one in my external interrupts, and in there I'm just gonna rename this and I'm gonna call it ext int0 test. All right. Now the reason why I'm going to make a test, here's what we want to do, and this is actually a practice that we actually follow and it works really well. We always have piece of code that we trust. So I always instruct people to make sure that we have one piece of code that actually exercises the circuit without any specific application. It just exercises the circuit. So if down the road we're actually in trouble, we just got really deep into the weeds, and we are just losing our bearings, and we don't know what the heck is going on, I can come back to this piece of code that I know it works. I've seen it working, okay? So this is my troubleshooting guide. This will make the circuit work once, so that down the road, if I ask you to connect an external interrupt on pin 0, and you can't make it work, you come back to this piece of code, because you know that this piece of code works, all right? So this is Troubleshooting Guide 101. Here we go. So I'm going to start with just the standard preamble. And then I'm gonna add something new. All right, so this is my library. And the reason why I wrote it like this, / whatever, is because my folder structure follows a very specific setup, right? Because right now, I'm writing a piece of code here. Right? I'm working on ext int test or whatever, right? So I'm working on a file. I think I called it, yeah, ext int0 test. Right? Here's what I'm writing. ... means one folder back. That's what that means. It says, go one folder back, and you're going to find a folder called library. Inside of that folder, you're going to find a file that is named that, and it's a header file. See that? I'm just instructing a machine how to find my file. So he goes ... which means here, you're going to find library, and inside of that, you're going to find the file you're looking for. Okay, now here's a little trick that actually works pretty good. If you double click, and just get it kind of like marked, right? If you right click now, and you say open, and it opens, it means that there is an actual physical connection between them. I can actually see it. Double click, right click, open, and if it doesn't open, you can't see it, so when you try to compile, it won't compile. All right, so I'm going to do it again so you can see it. You see what I'm talking about? I'm going to close that. So I go double click, right click, open, and it opens like that. That tells me that it can find it, okay?
So where are you saving this file?
I'm saving it in its own folder. So I'm working in this file that is saved inside of external interrupt folder. So you have your library folder where the header file was located. And now I am in a completely different folder working on my first piece of code. We'll get together in a little bit and fix that. So, okay? All right, once you're here, it's just time to follow the recipe. Here we go. Here's the recipe. Pound int ext0, void int ext0 isr, like that. And then we go main, and then you go adcon1 pcfg x equals f, and then you go tris b equals x1, and then we go, I think it was intcon GIE equals 1, intcon PEIE equals 1. Just going down the gauntlet, okay? So I'll go intcon int0 IE equals 1. We need the edge, right? First is the edge is on 2, intcon 2, and then we go int adg 0 equals 0, so that's a line. Peripheral, global, input, digital. This is int0 on, and that's it. How was that?
You have 2 incons, is that right?
Yeah, no, 3 incons. The location of those bits are always there, right? Okay. And here's where we're going to start to think. This is the part that I want you thinking, all right? I'll let you copy it. When we're done copying, we're going to start the thinking process right now, all right? This code will be online after the class, all right? So all the base code we do in class is provided to you. I want to make sure that you have at least a piece of code that works so that when you're doing your job, you're doing your labs, if you find yourself in the deep weeds and you can't make anything work, you can come back to this code and say, I know this code works, right? That's the idea behind it. But you see what we're doing. This is a recipe. I haven't done anything special. I haven't done anything intellectually new. This is the code that my ancestors used to do, you know, when the pterodactyls were doing microprocessor programming, this is what they wrote. And so it's just the microprocessor manufacturer gives me this. It's not like, wow, Alberto, you figured that out? No, I didn't. I just opened a book and I read it. And they told me, look, follow this sequence, Alberto. If you do this, it'll work. Okay, good. I'll follow that sequence. Okay, here's what I want you to pay attention to. Look at this. This code has no subroutine, right? There's no code in the subroutine. And there is no main code either. This is an expensive paperweight. It's not that expensive. It's $6 for the 4520, but you get my point. It's a microprocessor marvel that does absolutely nothing. So the system begins, it sets up the external circuit, and then does nothing. The main microprocessor is just, doing absolutely nothing. When you actually send an electrical event, in this case of falling edge, through pin B0, the circuit wakes up and executes nothing. See that? You here with me? So you have a circuit that is working properly, but there is no behavior out of it. Okay, so here comes the application. Whatever instructions we write now, from this point forward, this is the thinking part. This has nothing to do with the setup of the circuit, right? So this is nothing more than a mechanic that is about to fix a car, and he just rolled in all his nice little tools and he put them on the bench and he goes, I'm ready, let's begin. That's the let's begin portion, right? The beauty about this is that we can create, with one instruction, we can create a behavior that will tell me if this circuit is in fact working. Check this out. What if, as part of my application, this has nothing to do with the setup, this has nothing to do with the circuit, this is what to do with the circuit, right? This is, I loan you a hammer, you're going to use the hammer, what are we going to do with the hammer? We're going to kill a cockroach. Okay, that's your application, fantastic. That has nothing to do with, you know what, I'm going to put a nail on the wall. Okay, good, great, you're still using a hammer for doing that, right? The application is independent of the tool. So, I'm going to use this tool, this is how the tool gets set up, this is my base. I'm going to use this so that every time I press a button on pin B0, I will see pin B7 toggle. Just because. See that? I have a machinery. There's the machinery. How do you know this machinery is working? Unless you make the device behave in a way that you can see it. See that? So one way I can do this is by completely eliminating the necessity of if statements. I just simply do this. I'm going to go right here and I'm going to put a toggle instruction on somewhere. So that every time I press the button, the interrupt triggers and the LED switches. The interrupt detection is one system and the LED toggling is the application of it. Okay? So here we go. Here's the application. So I'm going to come here and I'm going to do this. Done. This is my application. I don't want you to confuse yourself with the reason of the existence of that instruction, right? I find myself marveling at what happens at the end of the semester when we're supposed to take all these subsystems and put them to work together. I notice that you put all the setup together and all the applications too. See that? If I have a different application and I'm bringing my hammer now, I got to make sure that whatever application I used in the past is left. Only the setup of my tool is what I bring with me. So keep in mind that this base code works without that output toggle. The output toggle is an excuse to see the system working. See that? Okay, good. Now that I have it here, I'm going to try to compile it. If we're lucky, it don't scream at us too much. It did. It doesn't like something, so let's see it. Invalid preprocessor directive. I think it's fuses or fuse. It says bound use delay. Which directive you don't like? I think it's called EXT. There it is. So it's called EXT. The 0 works for you? That's weird. It shouldn't. I think it's EXT and then EXT1 and EXT2. So if I make this 1, it will work. It'll work. All right, I'll fix the notes. It's EXT without the 0. right? So is ext0 is just ext. Okay, all right, so here we go.
Oh, it's crashed. That's fun.
Oh, that's really fun. Okay, so let me load this into a micro. So what I'm going to do now, I'm going to open Proteus, and I'm going to let you catch up now. So I'm going to go to Proteus. And I'm just going to open up, I'm going to create a new project. And I'm going to call the project External Interrupt Circuit. In this particular project name, you can put as many spaces as you want. This is a Microsoft application that can understand spacing without any troubles. And then I'm going to put this in my external interrupt folder. I want all of these things in the same folder. So that way I don't have this all mixed up. So I'm going to go extint and I'm going to call it external interrupt circuit. Okay, so I'm going to go next, 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 finish. And you should be here. All right, we've done this a little bit before. And then make a note here, because the most important part is make sure you disable the master clear pin. Right? So this is a master clear disable. So I'm disabling the master pin. I will give you this circuit too. Right? You're going to have access to this circuit as well. Okay. The next thing I'm going to do is I'm going to put a push button that I can use for testing purposes. Okay? So I'm going to take, and I'm going to just type the word button. You're going to have the opportunity to do this in just a little bit. I just want to make sure that we get this done. So I'm going to go here. I'm going to put my button. And I'm going to go press high, release low. So this is press high, release low. So this is a press high. Now, when you pick the resistors, I don't know. I always find like a generic resistor. The actual modeling works for me really well. So I always use a generic resistor. And pull-up resistors in this particular version of Proteus appears that 500 ohms is what works. In my day-to-day life, when we actually create our own circuits, we usually working at about 4.7K or even 1K. I never go this low, but for some odd reason, in the simulator, 500 ohms appears to work really well with the pull-up resistors. So I'm going to go with that. And I'm going to rotate this. And then I'm going to put a bidirectional pin. And I'm going to call this button. You can call this whatever you want. So I can call this like, I don't know. Yeah. Button 1 maybe, B1. All right, anyway. So I'll put one here. I'm going to call this B1. All right, so after we're done with the class, your job is going to be to try to just do this, all right? So we're going to just spend some time doing this. So don't panic yet. The next step in the process is that I want to make sure that my microprocessor is running at the speed that I advertised in my code. So I've been using 20 megahertz because it's a nice low speed. It's not very fast, so it's very well behaved. So I'm using 20 megahertz. So you double clicking here, and you make sure you get your 20 megahertz. Otherwise, your application looks like it's super slow if you don't update this number. And then I simply going to look for the hex file that I just created in my compiler. Okay? So that when you press and release, look at B7. See that? So if you look at the code, there is no main code that is doing this. Oh, this is annoying.
Click the little mouse to drag it.
Yeah, I'm going to do this. I'm just going to get this close. How about that? Okay? If you really look at it, there is nothing in main. There's no if statements, no input functions. We bypass all that. There's a circuit that is looking now. The circuit is doing the if. If you press do this, there is no if. The if is gone. I replaced, and I think that this is the take-home part. I replaced a piece of software with an actual circuit. See that? There's a guy that actually is one of the guys that actually were of great influence in the way that I write code. And this guy works at NASA, and he told me a very good embedded programmer is the one that exploits the hardware, not the guy that makes the most code. So if you can make your circuit behave without code, that's awesome. And I know that he was kind of like pushing the envelope, right? He's trying to make me think in very specific ways. But the reality is that hardware will never miss a piece of code, right? Hardware will behave like hardware. There's no way that your inverter is going to behave like anything else other than an inverter. It's a circuit. It was built for that purpose, right? While a piece of software is nothing more that changes the behavior of a circuit based on the executed code, right? So in the embedded arena, exploit the behavior of the hardware. If I can get rid of an if statement with an external interrupt, do it. See that? So there it is. Here is how int0 works. This is your base code. Now, we have all kinds of interesting applications. For example, last week we left you with a lab. The lab was to create a two-dimensional LED matrix, right? And the idea was to take an LED column and swap it, right? Like we're going to sweep it from left to right, back to the left, then create a row and go up and down. And it goes back and forth, up and down, back and forth, up and down. That was the idea behind it, right? What we're going to do this week for the lab is that we're going to add an external interrupt to it. So that when you press the button, the display sequence changes. Not with speed, but we're going to actually change the entire display behavior, right? So instead of showing a row that is going up and down, we're just going to make one LED go one at a time, all the way around the matrix, and then back and forth, right? So once I'll release the lab, you'll see what I have in store for you. But the idea is that now you start to see the reasons why these external interrupts are used in the industry. And it's because if you have a really large matrix that you're servicing, and you press the button, and it takes you 1 second to service the lights, that means that for 1 full second, any press that you make is ignored by the system because I am servicing the lights. But if you interrupt it, when I press the button, the interrupt changes. And when the interrupt changes, I already know what the new command is. So you could change the display in the middle of a display sequence. So we're going to be working on that next week. Okay? So that's the idea behind it. So, any questions on this one? Let me show you how int1 is done. All right? It's very easy. Here we go. Here's int1. So I'm going to take this guy. I'm going to copy it because we are the kings of copy-paste. Okay, so I'm going to copy. I'm going to give you this code, so don't panic yet. So I'm going to go close all, file new, external interrupt, and this is the example, the test on interrupt 1. So I'm going to hit that, and then I go 1, 1, next position, 1, 1, 3, done. That's it. Now, it looks like I'm doing magic. It's not. It's a recipe. I'll give you the recipe. This is the recipe. Yeah, go ahead.
No, it's supposed to be count 2. It's supposed to be count 2.
No. All the edges are on incon 2. That's a very good question, though. So let's take a look. So let's look at the table. So I'm going to go chapter 9. All right, here we go. So here is the on button. See it? That's on incon 0 or incon. Look at the edges. They're all here. Edge 0, edge 1, and edge 2, they're on incon 2.
Okay, yeah.
And then look at the 3 now. Mr. 3 has the on button for the other two guys. See how they're switched?
Yeah.
And so that's what this little recipe tells me, right? So I'm going to save this. I just compiled a new guy. And look, I'm going to take this guy from there. I'm going to delete this. And I'm going to put it on B1. Turn it on. It's not working. It's broken. See that? Got to troubleshoot it. B1 is ready, but it's not reading it. Let's take a look. Alright, so we got ext1, ext1, B7, input on 2. That's the edge. Okay, I believe something went wrong with incon 3, so I'm going to look. Is incon 3 FF0? Somebody check that for me. Let's take a look.
3 is
Okay. We have flag not EE. So let's go to incon 3. So I'm going to go to incon 3. So I have flag 0, 1, and 2. Flag 0, 1, and 2. And then I got a not used. And then I got 2 IPs. And then we got incon 3. Huh. No, I think it's that I did not change the code then, because everything looks good. That means that I never went here to swap the code. That's exactly right. See, still int 0. So I gotta go to int 1. And there it works. I just didn't swap the code. You see? Okay, so there is a file. One file is called int, it's called ext0. So one file is called int ext0 test. This creates a hex file when you compile, and this hex file you load into Proteus. And so the second file is called int ext1 test, and that creates its own hex file that I have to load into Proteus. I just forgot to load the right file inside of my circuit system. But you see the difference, right? It's just a couple of different spots. Now the question is, what happens when I start changing my application? And that's where the fun begins, right? When I really start changing my application. So can you do incon 3? Just copy paste and change it, right? So let's do 3, or incon 2, sorry. So you do copy. I'm going to close all. We'll find new. I'm going to call this unit 2. Paste. And then you go 2, 2. The next one. Edge 2, 2, Done. What's that? Switch my hardware. Switch my code. There's 2. Run it. There's your interrupt bar. Can you see that? Alright, here's what I'm going to do. I'm going to put this code online now. So you can have the circuit and all the code. Alright? So here we go. Dog cookies. In class code, and I'm gonna call these external interrupts. Edit. It's gonna simply erase all this and give you your new ones. So I'm gonna go to Spring library, that one. I'm going to give you external interrupts. You're going to have by type. You want 0, 1, and 3. And you want the circuit from Proteus, this one. So I'm going to take this external interrupt, and you should have it available now. So this setup, every time you're trying to do GPIOs and you're going to an external interrupt and you get in big trouble, you're starting to lose notion of what the heck is going on, go back to this spot. This will give you the very bare bones on how to set up any of those circuits, right? This is the basic code to set up the circuit. Does that make sense? All right, so that's that. Any questions on interrupts? What are they? How this external kind of work? All right, good. So we're done.